All right, welcome to AP Review Solutions number 10. Two problems. One is a simple harmonic motion problem. The other is a angular acceleration problem. Actually, I shouldn't say a rotational problem involving forces on an incline. Okay, so we've seen this problem kind of before in a recent homework, but I took that from the AP problem, so this is a slightly different one. So we have two graphs. So we have a mass on a spring oscillating up and down vertically. And we got two graphs of its motion, position and velocity. We can see that the period for both is around, right, 0.7, I should take that back, about 1 second. And that will come into play later. So they first want us to do potential energy as a function of time. Okay, so elastic potential energy, the easy approach, or I shouldn't say easy approach, you might think, okay, one approach I can do is equal to 1/2 Ka squared, where A is the amplitude. And I could get the amplitude from this. It goes between basically 0.5 and 1, so the amplitude is, if the rest position is at roughly right here, right, the amplitude is about 0.25. But then we could solve for K using the period equation. You could go that route, okay? So let me talk, since I mentioned that, because that'll come up later. We can find the spring constant based on the period, because we know period equals 2 pi radical m over k, okay? If we square both sides, we've got t squared equals 4 pi squared times m over k. Then it stands that k is going to be equal to 4 pi squared m over t squared. Okay, cross multiply, you can work that out. And t, again, is equal to 1 second. So you could go that route. I think the easier route is look at the velocity time graph and understand that the maximum potential. So we're going to look at maximum potential and then plot from there. So I can say, U max is going to be equal to Ke max, right? And they're just going to go back and forth between each other. So the easiest way to find K max is 1/2 mv max squared. Okay, so we see V max is right around 1.5 meters per second. We have the mass and that, and if you plug in the numbers, you get about a K max of 0.16, sorry, joules. Okay, so now we got our maximum K. Now we just got to get the right trig function. And I think the easiest way to look at the trig function is just look at the position, right? We're doing potential energy. Now you remember, you can't have negative potential energy here. It doesn't make sense to have it. So it's just going to oscillate between two extremes and 0, and center around 0. So when we go to do the graph, okay, keep that in mind. Technically, it's a sine squared function because to keep it always positive, all right? So we have 0. We want to go up here to some value. Let's say this was 0, 0.2, this would be 0.1, 0.15. Okay, so we set our potential energies right around 0.16. So at time 0, we see that we're not moving. So if we're not moving, we can make the inference that we're at a maximum potential energy. Or if you look up at the position graph, you would see that our position is not 0. It's at a maximum displacement, whether it's positive or negative. Okay, so we see that's at a negative, but that doesn't matter. So in other words, at time 0, we're going to have our maximum potential energy, which is at the 0.16. And then here, our velocity, or excuse me, before we get to 0.5, halfway, we see that we're at a maximum velocity, therefore a minimum potential. Okay, whoops, I should say we're down here. I gotta be careful, my zero's down here. And then we are going to be right here, we're going to be back in the opposite and after 1 second. So we're going to get a graph. Whoops, what this is doing, it's not. All right, that looks like this. Okay, so it's got to stay positive. We're reaching a max at every half second. Okay, and that corresponds to when the velocity is at a minimum. Okay, the next question asks about acceleration. Okay, and so I want to take a similar approach in the sense that we're going to find the maximum acceleration correspond and then put that at the right positions or at the right times, I should say, based on a period. And then we can look at the velocity time graph and understand that the acceleration, how it changes with time, goes by the slope of the velocity time graph. And that's really straightforward. So there's 3 points for this, and you got to do a lot of work for one of the points, and that's just simply getting the maximum acceleration. So A max, you're not going to get it from kinematics, you're not going to get it from delta V over T because it's not changing linearly. We've got to get it from Hooke's law, right? That's simply equal to the F of the spring divided by X. So what is the maximum force? Well, that's going to be K times the amplitude. Okay, I'm sorry, this should be M. F over M. So this is K times A over M. So I talked about finding K earlier. You didn't have to if you didn't take the 1/2 kx squared approach. But if you did, you have it. If you didn't, I showed you how to do it prior. Amplitude we talked about before, and then we would divide it by the mass. So that would give us our A max value. I think if we work it out, it's around 10 meters per second squared. Okay, now it's just an issue of how do we plot it in terms of time zero, etc. So let's go back up to the velocity time graph. So we see at the very beginning, at time zero, there is a steep slope. So it's accelerating here. It has a positive acceleration. Then at the 0.25 mark, the slope is 0. So we have 0 acceleration, then we go to negative. So we start with positive, go to 0, go to negative at the 0.5. So if we scroll down, okay, so our initial I said was positive. Let's just call that. All right, this will be 10, negative 10. We said we go to 0 about halfway, and then we're at the extreme negative there. So you can kind of fill it in and just make sure your extreme occur every half second. Okay, so that looks like a positive cosine curve. We didn't have to work that out beforehand. Okay, so let's go to the next problem. Problem 2, we have a ram, a wheel rolling down an incline. There is friction. It's at some angle, and eventually you're going to want us to find the acceleration. But before we do that, they want us to draw a force diagram acting through the center. No components, okay? So don't draw parallel and perpendicular components. That should be straight down. That's mg. We have the normal force, normal surface, right? And then there is friction, and the friction acts along the bottom here. Okay, whoops, that should be more tangent. So I think I misspoke and said it goes through the center. You put the arrows where they're acting. So these two are acting, I should say the normal force is acting down here. Okay, it's acting at the contact, force of friction at contact, but mg is acting at the center of mass. Okay, and then as the wheel rolls down a ramp, which force causes a change in angular velocity of the wheel with respect to its center of mass? Okay, so in other words, if it's initially not rolling and it's rolling, then there had to be something that caused it to angular accelerate. That's a torque, and the torque has to be a force times a distance in general at the lever arm. So the only force that has a lever arm about its center of mass is the force of friction. So you'd say the force of friction is causing the change in angular velocity because the force of friction is exerting a torque because there is a component of it that is a distance from the lever, or it has a lever arm or distance from the axis of rotation. Okay, so B is a little bit wordy and it's easy to get confused before you start. It's actually not a hard derivation, but you got to be careful about the friction. So okay, so it says the maximum, or the force of friction, static friction, is a percentage of the maximum, and this is key. 40% of the magnitude of the force or force component directed opposite the force of friction. Okay, what the heck are they talking about there? Well, we already know that the force of friction, actually I'm not going to scroll back up. Okay, we already know if this is the ramp that friction is acting that way. So if friction is acting that way, we want something that's opposite that. Well, that's obviously that. What force is that? That's mg sine theta. That's the parallel component of the weight. So what they're basically saying is that this value is 40% of this. So that's an important translation. So the force of friction in this case is 0.4 mg sine theta. All right, now we can go ahead and derive an equation for the acceleration. Okay, the acceleration is F net over m, right? What is going to be the F net? Well, it's just really these two forces. So it's mg sine theta minus 0.4 mg sine theta all over the mass. Now in problems that we did earlier in rotation, you weren't given this. You had to figure this out based on angular acceleration relating to that. Well, by them telling us that this value is 0.4, then it makes the problem a whole lot easier. The masses cancel out. 1 minus 0.4 is 0.6. So we end up with 0.6 g sine theta. Okay, it's as simple as that. All right, C. In a second experiment, we have the same ramp, but now we have a block of ice, the same mass, released from the same height, same instant, and they want to know which object reaches the bottom with the greatest, greater speed. Okay, well, we know the answer should be the block. Okay, it's not going to be the same. So explain in terms of forces and then explain it again in terms of energy. In terms of forces, I think is a lot easier. You can say the block has just the parallel component of gravity acting on it, whereas the wheel also has that force plus friction, so the friction is opposing it, so it can't accelerate as quickly. In terms of energy, it's a little bit more involved, but it's basically the same argument we make before when we talk about sliding versus rolling. So you would say both the block and the wheel experience the same potential energy, change in potential energy, therefore they both experience the same gain in kinetic energy. However, in the wheel, some of that kinetic energy is distributed to rotational and not translational, whereas in the block, all of it goes to translational. You would be incorrect in saying that the force of friction on here is dissipating energy. It doesn't work like that because the force of friction is doing no work on it. Because as it's acting, it's not acting over distance because it's not slipping. So we want to avoid that explanation. Okay, so if you have any questions, make sure to ask.